Lesson 40, electrical safety devices. We'll be able to describe the operation of several electrical safety devices. So we're going to describe three, or you could say four technical devices, because I'm going to break up one of them into two sections, because it's going to be like 2A and 2B, because they're pretty much the same thing, but we're going to pretty much be going through three main types of safety device. But I'm going to talk about that after I quickly talked about what we did last lesson. Last lesson we talked about, after we talked about what double insulation means. Here's a symbol, by the way. That's part of the scavenger hunt. You need to find a device with this symbol. I actually think it's pretty easy to find. You should be able to do it. We talked about how cars ground, but when they ground it to the electronics. And then we talked to the frame of the car. Then we talked about, what does electricity do on the body? We said that the first thing is the body uses electricity to send information via nerves. Now, nerves are cells, and what they do is they send electricity down the nerve, and then when they connect to a new nerve, they use stuff like synapses, and they send a little bit of information. But they essentially still conduct electricity. They still send electricity. It's very, very small, but they do. So, and these do two things. They can send information to your brain, but they also send information to your muscles and tell your muscles whether to contract or not. And this can be quite bad if you're getting shocked with electricity. AC current and DC to a degree, but mostly AC current, can cause those muscles to twitch. We said that when you get applied with electricity from outside of your body, we call that an electric shock. We said that sometimes it can, if you have high DC voltage or high AC voltage, you can die. But we figured out that it's a bit weird, because you can actually survive static shocks really easily. And so the overall idea that I said is, be careful. Electric shocks and electrocution, like, there are lots of things that can differ, whether it's going to be a painful, ow, I zapped myself, to, ooh, ow, I've been knocked unconscious, to, oh my God, I'm dead. And those things that change that are the voltage. High voltage is going to be very bad. If you get a high voltage, you might get a high enough voltage that it can burn through your skin. You might get a high enough voltage that it can, vaporize flesh, but you might just have a high enough voltage, it might be just a low voltage. It doesn't make a difference. It also depends on the resistance of your body, the current that the electricity has, the path through your body, and the time of exposure. We said that your body has a resistance of 1,000,000 ohms when it's dry, but when it's wet, it starts to go down. And actually, once your body is being pierced, because maybe it breaks your skin because it's got a high enough voltage, then most of these things sort of go away. So you've got to work out for it. This is one of the reasons why you should never use like a hairdryer or any kind of electrical device while you're in the bathtub. It's also why you got to be careful in pools with like underwater lighting and stuff, because you don't want that mixing with the water. Okay, current in your body. It's bad to have high current. If you get a high current across your chest, then you can have fibrillation, which is where your chest muscles stop beating in unison. Ultimately, when you hit someone with a high current, you can cause pain, then you can cause their muscles to contract and spasm, and they will then remain paralyzed until you remove that electricity. This is a great way to stop an intruder coming into your house with a taser. But if you've accidentally grabbed a wire and you could then get paralyzed and you can't, your hand muscles contract, you can't let go of that wire. So it can be quite dangerous too. We talked about how you really don't want the current to go across your heart, because usually current will try to get to the path of to least resistance. So if you're touching something it might just go down one side of your body. But if you're holding onto a metal rail, or if you've got 1 foot off the air, it may go across your chest, which might put your heart muscle into fibrillation, and then yeah, your heart doesn't perform as well. And again, this also all comes back down to time. The shorter your time of exposure, the less danger. Now, I didn't finish off this, but I wanted to finish off this effects on the body to what should you do if someone does get an electric shock. Now, you don't like this is not really physics, this is more like first aid, but considering we're on the topic, we should still address this. If you see someone that has experienced a shock, the very first thing you should do is you need to, and this is probably the most important thing, ensure that it's safe to help. Disconnect the electricity or move the victim away with an insulated material. In this picture here, you can see, obviously it's pretty fake because, well, I think, it could be right, but the idea is that she's got rubber-soled shoes that's going to stop her from conducting electricity. She's got a plastic pole. She's got gloves. She's got lots of ways to make her very highly resistant as she removes the electrical device. It'd be a bad idea. Oh no, my friend's just been electrocuted, and you run in to go save them, only to find yourself getting electrocuted. If it's a down power line, you should call up 000, tell them that they need to quickly come and disconnect the power. If it's at home, and the safety devices in your home have been already shut off the power, then you need to remove them with a pole, or remove the device, or unplug the device, or something like that. You should never, by the way, put a fork in a toaster to get toast out, because it's a great way to get yourself electrocuted and die. Check the person's response. Are they breathing? If they're not breathing, because remember, a lot of the times they may be suffering fibrillation, so their heart might not be pumping. You may have to perform CPR if you know CPR. If you don't know CPR, give 000 a call. You need to call them anyway to get an ambulance. And the advantage of that is that the people on the other end of the phone line, if you say, my friend's been electrocuted, they'll probably say, you need to perform CPR. They'll say, do you know how? If you say no, then they'll instruct you how to do it. If they are breathing readily, you need to put their burns under water and apply a bandage with no ointment. That might be because, of course, if you've touched something that's electrified, then you're probably going to burn your hand. Because remember, high voltage is going to mean that it's going to singe some skin. If they've fallen from a height, so let's just say they were up a ladder cleaning the gutters and accidentally touched the wire that goes into the house, and for some reason that piece of wire that they touched was like unsheathed, like didn't have any plastic around it. They got electrocuted, they fell off the ladder. Don't move them, because if you move them and they've broken their neck, then it's going to be bad times. And of course, talk calmly and reassuringly to the person. You don't need to know, as this won't be on the test. This won't be on the test. But why I'm telling you this is because it's good to know this kind of information in case you do have a friend that he's electrocuted. Like, it's just a good first aid thing to know. We're also going to be doing like some stuff with electricity with some pracs next week. Obviously, don't fiddle around with the circuit if it's plugged into the electricity, and don't put things directly into, like, don't put a wire directly into a power point, because yeah, you could die. It's just obvious. So yeah, this is summarizing it. These are the main things that change whether or not how bad your shock is. The voltage, how much energy are you hitting the person with? The resistance of the body, how hard is it for that voltage and current to get into your body? If it does get into your body, how much current is there? Remember, if you've got dry skin, or if you've got plastic around your hand because you're wearing gloves, you probably won't receive that much current through your body anyway if you do get an electric shock. which path does the electricity follow, and how long are you exposed for? So what can cause these? This is now today's lesson. What can cause these electrical shocks? What can lead to these bad things happening in your body? Well, here's two relatively unsafe electrical practices. On the left, we've got an overloaded circuit, and that's, you can see this is one of the ones you want to avoid doing. And I have to admit, I am guilty. I have put a double adapter on a power board once, but yeah, you really want to avoid this. This is like a power board that goes into another power board here, and then you've got a doubler adapter on that power board as well. Oh wow, hold on. You've got a power board connected to a double adapter, which is connected to a power board. That's crazy. Okay. The idea is you're trying to draw too much current, too much voltage through that one on the left. This is why this one's unsafe. Can someone tell me, why is this one on the right unsafe? Why is having frayed electrical cords, why would that be an unsafe thing? Can someone either say, you know what, I'm going to unmute you. Can someone tell me why the one on the right is unsafe? Don't all speak at once. I can hear Lucius chewing.
It's because the conductor is exposed.
Yeah, beautiful. Thank you, Lucius. That's all. You weren't chewing at all. You were just thinking. Yeah. I've just muted everyone again. There you go. Be happy. That's because the conductors are exposed. You've got the positive and the negative. You've now got a way that you can just easily, with a touch of a finger, short circuit that circuit. So any time you've got frayed wires or overloading a circuit, you've got something which can cause some harm. You've got something which can lead to someone suffering an electric shock. Now, let's talk about the issue here. So here we've got our toaster from earlier, which had some issues. We can see here that we've got a wire here that's connecting in the active wire, the electrified wire, to the outside of the case. Now we've got a person here that's now trying to use that toaster. The broken hat toaster has two parts down to get to neutral or ground. The toaster can either go through this circuit here to get back to ground, or instead it can go into the electricity can go, whoopsies, into the to the metal of the toaster and through the person's body to get to ground. And that's two bad ways. And obviously the one on the left, the one that goes through the person, is going to lead to them getting electrocuted. Well, it's going to lead to them having an electric shock. If it travels via the person, they receive a nasty shock. So what kind of safety features exist to prevent this person getting a nasty shock? Or if they do get a nasty shock, to prevent that nasty shock going for a very long time? Some of those issues are, one, grounding. We've already discussed grounding, but just so you remember, grounding is where you offer two parts. One is for the electricity to go out to the person. The other one is through a grounding wire, which goes back out to the ground via the electricity, which is why we've got the grounding stake outside of our house. That's one way. So you're trying to say, hey, grab a look at this. We've got a grounding stake. You know, it's a straight metal wire straight to the ground. It's going to be a lot more easy for electricity to go through metal than it is to go through the human body, because it's got a million ohms of resistance in there. What happens if, let's say what happens if maybe your grounding stake doesn't work? Is there another way that you can save something? Yes, there are. There are fuses and circuit breakers which cut the electricity before it gets too much. Is there another way? Well, yeah, there is a residual current device, and these residual current devices measure the incoming voltage, incoming current, and outgoing current. Make sure they're the same. And if they're not, something's gone wrong. We're going to talk about each of these things in this next couple of minutes. I know we've already talked about grounding before, but I think it'll be a good chance just to recap it. I do want to point out one thing that I think I failed to teach you guys, which is this. Let's ignore this dude for a second. What's another issue that can occur with another issue that can occur when you have a problem like this? When you have a faulty electrical device, is you could end up instead of having an issue where like the electricity someone gets shocked by the electricity, you could have an issue where yeah, I actually got a fire. I was almost going to ask you guys this question, but yeah, if an electrical device is here and I accidentally, this picture up there, if I accidentally if I'm like, oh, this newspaper is a great path to get from the high voltage here back to ground. So what it will do is there'll be a spark that will go over to the newspaper. Now, if that spark is energetic enough, it might cause the newspaper to catch on fire. And if the newspaper catches on fire, then you might end up setting the whole house on fire. You might think, oh, well, that's, that would be obvious if that was happening. It's like, yeah, sure, you're right. But if you're in the ceiling of a house, right? Say you're in the ceiling of a house and a rat has come along, and they do this, and this rat's come along and they've chewed through the wire. So now the wire is still working, but it's every so often it's sending off sparks off this wire. Then that could very easily cause the insulation in your ceiling to catch on fire, and then next thing you know, you got your whole house on fire. So I guess one of the more bigger ways that people die from electricity is not necessarily by getting an electric shock. Probably the more dangerous one is when a device that's broken, that you don't know that's broken, starts sparking, and then next thing you know, you've got yourself an electrical fire. And yeah, once you've got a fire, if it's in the roof or if it's behind the wall and you don't see it, you could be in for some very bad times because you can't see the fire before it's already happening. This is why it's so important to have smoke alarms. Some people might think, I don't need you probably no one here would think that, but you might think smoke alarms are only good if you accidentally like leave something on in the oven. It's like, yeah, but that's true. But if there's an electrical fire because a spark happens in your ceiling, you want to know about it as soon as possible. Let's talk about grounding. Grounding rod, as I've said already, is the first safety device. As stated earlier from previous lessons, I'm not going to go back over this too much. It provides an alternate path of very low resistance. Ultimately, if the electricity can choose between going through a metal wire to get to the ground or going through a highly resistant human being to get to the ground, it's going to take the metal wire, which is how you can survive grounding issues. You might feel a little tingle, but trust, because you're still feeling some current go through, there's probably not as much that's going through the wire. As current moves through it, it will generate a large amount of current. Think about it. You've got a wave that's like, oh, there's very low resistance. If I have very low resistance, if I have 230 volts and I'm only going through, let's say I've got the resistance is like, is 0.1 amps or something, it's very, it's a very low resistance, then that means you're going to have a very high current. The current's going to be 2,300 amps. You're going to have a very high current going through that wire. Low resistance means high current. That's really important because I'm going to explain why we care about this in a second. The reason why, knowing that there's such a high current going through this wire, is because it will help us explain how these other electrical devices work. So let's just say the worst things happen. You've touched, a wire in your toaster is broken, and suddenly a bunch of electricity is going to ground instead of going through that toaster. It's a short circuit. So because it's a short circuit, it's got a lot of current going through it. So now you've got this short circuit happening in this toaster. Good news for you is it's going to ground. It's going to the ground wire, so you're not going to get electrocuted. Bad news for you is that you don't know that this is happening. You don't know that your toaster is broken. And, if your ground wire has an issue, then you could get sparks. So you have a broken thing. So what's the next step? How do we stop a bunch of electricity going into the ground? What we use our second device, which is called a fuse. Now, fuses is a length of wire designed to melt or break. And when that fuse breaks, so it's a fuse of length of wire designed to melt, so breaking a circuit when the current passes through it goes above a certain level. This means if something is shorting to ground, then it won't do it for long. Fuses are cheap and still found in many cars. So here's some examples of some fuses, and that's what a fuse looks like. The idea is, if you look at this fuse here, it's just a very thin wire. Now, if you start to flood a bunch of high current through that wire, then that high current is going to get very, very hot. And if that gets very, very hot, what it will do is it will melt. A fuse is a length of wire designed to melt. And so when it receives high current, it will melt. And when it melts, then you've got one wire here that's melted. They're not connecting. So now there is no more current going through the circuit. And that's how fuses are designed to work. They're designed to melt to stop things from going any worse. They're designed to melt so that therefore no current can get moved, no current can move, no current can transfer. You can almost see as well that the picture of a fuse in a circuit is actually very similar to what a fuse actually looks like. It's usually a cylinder with a small, tiny, thin bit of wire through it. And some electrical devices actually have fuses built into them so that you can change them out if they do break. Now, fuses don't get used that much anymore because they still take a little bit of time. They're not instantaneous. They usually take maybe 10 to 15 milliseconds to break with. And if you're getting electrocuted with 20 amps, you want that thing to be breaking as quickly as possible. But they are cheap. So and that's why they used to be called fuse boxes, because they would have fuses in them. But nowadays we don't really use fuses anymore. As I said, they're still used in cars, but we don't really use fuses as much as we used to. And of course, once a fuse is used, that's it. Once it's done, you can't rejoin the wires. It's broken. You've got to throw it away and buy a new fuse. Obviously, fuses don't break too often, so you're probably not in too much trouble. But yeah, on the right, by the way, are 3 fuses with different amps. And of course, these different amps mean that they will break at different points. Because if you've got an electrical device that needs that needs 10 amps, it doesn't make sense putting a 3 amp fuse in it because it will melt and break. So what's the modern equivalent of a fuse? The modern equivalent of a fuse is called a circuit breaker. A circuit breaker is an automatic switch designed to protect an electrical device from damage caused by overload or a short circuit. once you short circuit to ground or you overload something, ultimately when there is too much current, if there's too much current, then this will short it. The circuit breaker will say no, stop, and it will cut off. By the way, just quickly, this, where is it? This on the left, this is going to draw a high current because there are so many different circuits here, each in parallel, each asking for 230 volts. So it's going to draw a high current. So that's probably going to trip a circuit breaker if you're not careful. So like a fuse, it switches off a circuit when the current is too high. The advantages of a circuit breaker over a fuse, and I've written both of these as number 2 because ultimately they both do the same thing. They both switch off a circuit when the current gets too high. The advantage is, of course, is it's faster. It happens in like, millionth of a second, and the fuse can be reset. So let's just say you're finished. Your toast is broken. You throw the toaster in the bin. You reset the circuit breaker, and you can now use electricity. Whereas if you break a fuse, then you throw away the toaster, you're then going to go buy a new fuse. So it could be out of electricity. Usually you'll have backup fuses, but if you don't, you're in trouble. So you should. That's why circuit breakers are usually the better thing. And most, I think pretty much it'll be very difficult to find switchboards with fuses in them anymore. Most of the time they're just circuit breakers now. I still think it's important to talk about fuses because a lot of you guys can make sense of that. Oh, current gets too high because something bad's happening. Then the wire gets too hot. The wire gets too hot. It melts. The wire melts. No more current. I think it's called, I think there's a technical name for it. I think it's called a negative feedback loop. But I always get those two things confused. So I don't know. Maybe someone smarter than me in the chat can tell me if it's called a negative feedback loop. So how does a circuit breaker work? You don't really need to know how it works too much, but I do want to quickly show you anyway. This is one from the book. Now, how does it work? Okay, so you've got here a let's see, where is it? Yeah, okay. So you've got here a little lever. I don't know how to best describe it. This here in green is a lever, okay? And if you push that lever, you can see that it breaks the circuit here, okay? So the circuit's connected here, it's not connected here. If you push the lever, the circuit breaks, okay? That's the first part you need to understand. If you push the lever, the circuit breaks. Now, the next step is to then say, okay, well, how could we, and well, what's normally happening? Normally what happens is you've got, look at this, you've got this wire comes up, through, across, down, through this break and into the rest of the house. Okay, so when this gets broken, the electricity can come up to here, but it can't get to the rest of the house because it's now broken. Okay, it doesn't work anymore. Now, what happens is that how do you push this lever then? What's the big deal with pushing this lever? This lever gets pushed by this. This is a heating coil. Now the heating coil is attached to the wire itself. So the mains electricity. So if suddenly it starts to get a lot of current, that heating coil will heat up. And it just so happens that when that heating coil heats up, it causes this metal to bend. That's because this metal is a bimetallic strip. Bimetallic strips are kind of cool. As they heat up, they bend and they warp and they change shape. And that will cause it to bend and break the circuit. When you've fixed everything and everything's safe, what you would do is the switch, the big switch thing, will push this back to the left and will reset the circuit. So you can reset this just in case. I think you would push, I'm trying to see if it says what you would push. It doesn't sort of say how to reset it, but yeah, ultimately that's how it gets reset. As I said, you don't need to know how this works. You're not going to be tested on this. You're not going to be asked to recreate it. All I'm trying to show you guys though, and the main part you need to understand is when the current gets too high, the switch turns off the system. This is actually a thermal circuit breaker. There are other types of circuit breakers like magnetic ones. Magnetic ones, when the current gets too high, it cranks up an electromagnet and the electromagnet switches off. It does the same thing, it switches the lever open. Most modern circuit breakers are actually a mixture of both. And I was looking at it, was very interesting to see why. It's because these heating rods are really good for low, when the current's high, but it's not too high, and it will switch it off, whereas magnetic ones are really good if you a quick sudden burst of electricity, this will cut it off. So that's what a circuit breaker is. The main thing about a circuit breaker and the fuse is it cuts off the current, it cuts off the electricity when the current gets too high. And the reason the current would get too high is if there's a short circuit to ground or a short circuit at all. But what if there's a scenario, what if the worst possible scenario happened where your ground wire isn't working? Let's just say your ground stake has fallen out because it's been a flood, and so you don't actually have a good way to get to ground. So instead, the electricity is going to go through a person, and maybe that person's got a high resistance, so it doesn't trip the circuit breaker. Is there another safety device? And there is. The next safety device, which is also included in most safety boards, is a safety switch, and what it does is called a residual current device. These are found on devices like in this special PowerPoint switch, or in a lot of, for example, my switchboards. One of my switchboards has this little yellow light, orange light to say that it's safe, and it's got these residual current devices. What they do is they measure the amount of current going in and the amount of current coming out of the socket. And if these two aren't equal, the electricity is cut. Let me show you an example here. Okay, it's going to be a really basic example, but still. We've got here a washing machine. Yeah. 4 amps are going into that washing machine via the hot wire. Yeah, we would call that the hot. No, what do we call this? We call this the active wire. And 4 amps are coming out. We would call that the neutral wire. And then you've got the ground wire, which has got the ground wire, which doesn't go through this device, has got 0 volts. Nothing's coming out of that ground wire. Everything's happy. The reason this device is happy is because the current at the top is the same as the current at the bottom. These two values are the same. So now let's say that there's a break in the circuit. Okay, there's a break in the circuit, and for some reason, 1 amp is getting loose. 1 amp is going through to ground, or maybe worst case scenario, 1 amp is getting conducted through a human being, or maybe 1 amp is just getting conducted through the washing machine into the floor, which is just still, whatever it is, it's not good because that could cause a fire as well. So, but what the device does is it says, hey, the active wire, that's still got 4 amps going in, but this neutral wire doesn't have 4 amps going out. It only has 3 amps. You might think, this, by the way, they have to be the same because you know already from Kirchhoff's law, the current in has to equal the current out. So if these two aren't the same, the device goes, there must be electricity getting lost somewhere, right? There must be electricity that's not coming back where it should be. So it says these two values are unequal, I'm not happy, and it will shut off the current. The current gets shut off. And then you've got to reset it once everything's safe. And then that will protect someone when they are getting electrocuted. Let's just say there's no grounding wire, so there's no low resistance, so your fuse and your earth aren't helping you out. Your residual current device, or RCD as the company called, will save you. And a lot of devices will have RCD. A lot of power devices will have an RCD device in it. So yeah, but there's also a couple of them in your switchboard as well. I think they will trigger a switch the same way that it's the same sort of idea that will happen with a circuit breaker. You can reset that switch afterwards. Now, obviously, actually, it's a little bit more complicated with some magnetic fields and stuff that I'm like, and this is straight from your textbook. But to be honest with you, I thought it was easier to explain with just smiley faces and sad faces. And I think you don't really, luckily for you guys, you're not doing year 12 physics yet, so you don't need to know how magnetic fields work exactly and with electricity. So I'm happy just to ignore this picture here and just move on. The main idea, I guess, is this here. If the in and out are the same, nothing happens. If the in is greater than the out, then what that's going to do is it's going to turn off a switch. It's going to turn off both of these switches if that's the case. What I'm going to do now, so those are the 3 devices. Let's talk about them again real quick. We've got grounding, which is great. It gives an alternate path for the electricity to get down that isn't through human being, that isn't through a newspaper. It's through the wiring in the house itself. And it's got a really, really high current. That really, really high current is enough to melt a fuse and therefore stop the circuit running at all, or it's enough to trip a circuit breaker, which might work in some way to prevent high current from getting past. Fuses have to be bought by a new one, but they're cheap, whereas a circuit breaker can just be reset, and it works faster than a fuse can. Residual current devices measure the amount in versus the amount out, and when they're not the same, what they do is they say something's wrong and they switch off the electricity. What I'd like you guys to do now is, could I get you in chat to write down one thing that you can see here that is unsafe? This is the very last, second to the last thing that I want to do before I finish up. What's one thing in this that is unsafe? Someone said something good. Got 3 answers. Let's see. Okay, wow, a lot of answers. We've got, okay, so first one we've got here is the dog is biting a wire. Yep, that's pretty bad because the dog bites a wire, then they can get electrocuted. Got a frayed cord, current from the circuit, electrical device near the bathtub. Yep, bad idea. Yep, the bath near the water, dog chewing cable. Give me something else. Give me something that someone else hasn't said already. What's something else that you can see in this circuit that's a bit dangerous? If you want, you can unmute yourself, that's okay. Well, here we go. Dude tripping over the cord. Yeah, so obviously that's one of the reasons why you don't want to have cords running everywhere. One, because people can trip over them, and that'd be bad because if they fall down and hit their head, they could get very injured. But another reason as well is because, yeah, if someone trips over a cord, then they could potentially rip that cord out of the wire, out of the circuit, and then that could then lead to them getting electrocuted. Anything else that you guys can see? Multiple devices plugged into one power point. Perfect. That's exactly what I was looking for. All right, before I finish up, I want to show you a fuse in action. Turning on a device that's broken. Well, where's that? Actually, I haven't seen. Where's the device that's broken? Oh, is it talking about the lamp, like the light bulb? Yeah, you're right. You shouldn't try and turn on a device that's broken because it's probably broken for a reason. Can't remember what this one here is with the bathtub on the right here. This picture here. I don't know what's wrong with that one there, but yeah. Okay, so what I want to do now is I'm going to quickly share something different with you. I'm going to share this circuit here just because I think this is interesting. This here is a FET simulation. I might get you guys to play around with this later. I might even get you guys to play around with this on Friday. That'd be something that'd be good to do. This is a power supply. It's supplying 10,000 volts. And then I've got this resistor here. This is a powerful 1,000 ohm resistor. 10,000 divided by 1,000, which means that the current should be 10 amps, correct? Yep, look at that, current 10 amps, got a high current going through here. Now, let's say that something really bad happens, right? Let's say that there is a short circuit. So instead of current going through the circuit, let's say current can get short circuited and go around the circuit. What's going to happen? Can I get some predictions? What do you guys think is going to happen when I short circuit this circuit? Someone say either out loud or in chat. What's going to happen when I short circuit this? It'll burn? Yeah, probably burn. Let's check it out. And bang. And I've got a fire. And that's really bad. Obviously, that's bad because I've short-circuited something. So, how could I stop this from happening? Well, let's put a fuse in. This fuse is going to sit here. And most of the time, that fuse is going to do absolutely nothing. Oh, shit. Crap. Let's see if I can. Why did that break? That shouldn't have. Oh, yeah, okay. Okay, let's do. Okay, let's do this. There we go. Look at that. I fixed it. Now, most of the time, that fuse is doing absolutely nothing, right? It's just sitting in there, carrying the current, whatever. But if I introduce this time a short circuit, ready, and now, instead of the battery catching on fire because it gets hot and that current keeps running, it turns itself off. The reason it turned itself off is because, let me just get rid of this again. I set that circuit to go off at 10.5 amps. This is like 7 million amps or something. So that's because obviously these wires are very, very low resistance. So the second it goes past, this is going to break again because I haven't fixed it. the second it goes past, we'll say 12 amps, it's going to break. And we will. Oh, it's still here. And that's okay, because we would expect that normally, this is normally 10 amps. So ultimately, whenever you see, it goes, whenever you see something that's more than 10 amps, I want you to break. And it doesn't always work. Oh, and that's fine. If I was to do, yeah, but like, that's why you also want to make sure that it's set in the right place. If I was to connect this by here, bypass it, short circuit, bang, fuse breaks. So it's just an interesting, I just wanted to show you guys that that's what a fuse is designed to do, to stop a short circuit. It breaks, and the second it breaks, no more current can move.